Well, good morning, guys. Excuse me. Good morning, guys, and welcome into class. Hope things go better than my first sentence did today. Kind of nippy this morning. Anyway, hope everybody's doing okay, and we're ready to have a big class this morning. We got a tough one this morning. This is probably the toughest chapter we have in this whole course. And so let's go ahead and jump into it, give it plenty of time. Go ahead and share out my screen and adjust this just a little bit so that we can get this done. And so this week we're going to tackle recursion and algorithms. This would be the math segment of our program. So right off the bat, my first apology today is that I misspelled algorithms. There is no U in algorithms. I've made the correction for the future, but future sections, but I did not change it for this one since we're so close to the end here. Anyway, I need to learn how to spell a little better. And it's a pretty tough unit. It's going to take some concentration on all of our parts to kind of understand this. We're going to use some of the natural patterns that we can find in numbers as a means to program something that we want to program in Python. And so there's two big math problems and a puzzle game that we're going to work on this week that I think hopefully you'll find it interesting. To me, it is very interesting. So there's only 12 pages, if I'm right, in chapter 13. So it doesn't take a whole long time to read it, but I do think you're going to need to study it. There's some parts in it that are going to be head scratchers, and you're going to have to think about them a little bit. We have a discussion post this week, as well as two labs. I worked on these labs on Monday to kind of refresh my memory. They're the discovery type labs. You're really going to look at programming that the book provides and make a couple of adjustments to some variables, some parameters in methods. But other than that, it is pretty much, I think you put in one print function in one of the labs, but you don't have a whole lot of programming to do, but you will have the opportunity to read these programs that we're going to discuss today and see how they work. Also, there is a quiz, one more quiz. Where's the next to last unit? Only one more unit next week, and then 2 weeks from today we'll be talking, or actually you'll be taking the final exam. Now, of most importance today is unit test 4. It is open. Today is the last day. I just sent you an email to remind you. It has been open since Monday. And I think out of the 4 sections, I've had maybe 8 or 10 students take it. And that's not many when you have about 60 students combined and about 63 students combined in the 4 sections. And we've already had somebody ace it, somebody in this very class. I won't call him out. I don't want to embarrass anybody, but congratulations. And so that's really good. And I want to make sure that I correct something I said wrong last week. I think I said that there was all multiple choice and true false. There are actually 3 fill in the blank questions in there. I thought that I had taken them out, and evidently in my haste to get the exam done, I left them in, and I apologize for that, but they're not too tough compared to the previous exam that had a ton of fill in the blank. This one only has 3, and since not everybody gets all the questions, you may just get 1 or 2 of those fill in the blank questions, so it won't be too bad. I have no idea about the curve because this is kind of a new venture on this test, something new we put together. So we'll see how that goes. But it looks like the grades are going to be pretty good. I thought they would be pretty good because of the more multiple choice questions, but had a guy in yesterday's class make a 50 on it. So who knows? You know, you got to know your stuff, even with multiple choice and true false questions. So I guess you guys know that already, but get that test done today by midnight tonight. and then all the other stuff in Unit 13 is due on Sunday. Next week, we'll take on classes. We'll define and use our own classes. We've done a little bit of work in classes so far in this course. This is important to me because in looking at other Python projects on the internet, I've seen lots and lots and lots of custom classes. There are classes that people write for Python that are not part of the overall distribution of Python, and you can acquire those on the internet and incorporate them into your projects. And that's one of the nice things about open source and sharing. And so the last unit is real important to understand how classes work and how to write your own class. And possibly some of you guys will be sharing some of your creative work on the internet for other folks as well. So that's next week. And then 2 weeks, we have the final exam. It will be a Q&A test. It will include questions from all the 12 units that have been covered in the 4 unit tests, plus Unit 13 and 14. There'll be a few questions from Units 13 and 14 that you haven't seen. So, and there will be fill in the blank questions on that one as well. No discussion questions. We have those in other classes. Man, I don't write those into my tests. They're hard to grade, hard to take. I don't know. I would much rather test a different way. So, but we do have fill in the blank. The thing about fill in the blank is it's a good challenge for the students and it's good for the instructor because we know exactly where we stand. You can guess for a while, but in life, eventually you're going to have to actually know something. And so the fill in the blank questions really kind of help us understand whether we actually know it or not. So that's coming up. Has anybody got any questions about the agenda for this class? There have been a bunch of announcements coming out from the college. One I got this morning today over at the ARC at McAllister Square. Any student can walk in and get their COVID shot. And they're going to be over there. Walgreens is over there giving COVID shots until 6 o'clock today. So if you haven't started your COVID vaccines, you need to go over there. I kind of think it's Moderna, but I'm not sure whether it's Moderna or Pfizer. It's definitely not Johnson & Johnson. So somebody just put up on the chat, it's Moderna. So if you haven't heard that, I wanted to pass that word out. And also I wanted to share with you, and hopefully you've seen an announcement on it. The student showcase is today at 6 o'clock. Normally this is a live event, and I think this is the 4th year we've done it, but it is a chance for different departments across the college to highlight some of the work that their students have done. And in the past, it's pretty much been dominated by the visual arts people and some of the fine arts people. Not so much from technology. There's a few technology projects normally every year, but not nearly as much as the people that paint and draw and sculpt and plays. There'll be a performance, probably a little play, maybe a speech or two. But you might enjoy that. It's at 6 o'clock. It's on Zoom, and I don't have a link for it. But if anybody is interested, send me an email, and I'll find a link for it. I think I have it in an email, but I'm going to try to make it this year because I haven't. I missed it last year, and I should have been there. So those are some things going on besides class, and we need those to help us be well-rounded and all that. So let's go ahead and get started in Unit 13, how to work with recursion and algorithms. Some of you guys will remember this from previous math classes. In yesterday's class, one of the students was telling us in the chat that he had seen some of this in some other math classes. But there are certain patterns that we have in numbers, and we're going to play around with those some today. We'll talk about what an algorithm is, and we're also going to talk about the stack. The stack is going to be very important to understanding the difference between a recursive function and an iterative function. Up to now, we have been doing everything as iterative functions, basically for loops and while loops. are the majority of our repetitive functions, okay? Now we're going to learn how to do it a different way, which is called recursive function. We'll learn what the base case is in a recursive function and also what a deferred action is. And you're wondering, okay, why do we care about another way to write functions? Well, in some cases, a very limited, in my opinion, number of cases, recursive functions may be helpful because you can normally write them in very few lines of code. They're very short. But the problem is they just eat up system resources, and you can actually, if you have an infinite repetition in a recursive function, you can run out of resources. And you're going to learn that and actually practice some of that in the lab. So you'll see what we're talking about as we get through this unit. So right off the bat, what is an algorithm? In this chapter, our writers define an algorithm as a step-by-step series of operations that perform calculations, process data, and automate reasoning tasks. And I have to admit, that's a pretty good definition. I like that definition. I did go out and see if I could find another one. I found one I like a little bit. It's a little bit more academic on Wikipedia, but I think we need to understand what an algorithm is so we realize it's nothing to be scared of. In mathematics and computer science, an algorithm is a finite sequence of well-defined computer implementable instructions, typically to solve a class of problems or to solve a computation. That is a lot of fancy words that basically says the same thing as the writer of our textbook. So we do algorithms all the time in daily life. When you do a math equation, you're basically doing an algorithm. If you're balancing your checkbook, you're basically doing an algorithm. So it's nothing really to get too excited about. Now, we are going to talk a lot today about stack. So I think we need to focus on what that actually means. We studied stack back in Unit 5, and I hope you're saying, oh, wait a minute, I remember that. Because in Unit 5, the definition was that a stack is a list of functions in the reverse order in which they're called. Remember, we had that feature of the debugger in our idle compiler where we could go into the debugger and look at stack view and see all of the functions in reverse order that have been stacked up there. So I found a nice little, I guess it's what, 2 sentences, short paragraph at George Mason University's website. Some smart guy in their computer science department wrote it. The function call stack, often referred to as the call stack or the stack, is responsible for maintaining the local variables and parameters during function execution. It is often only alluded to in textbooks, but plays a central role in the execution of computer programs written in just about all modern programming languages. So just realize that the stack takes memory, and some of the functions that are being put in the stack take a lot of memory. So we have to be aware of the stack, and also our use of the stack, which is totally in the background. We can't see it, but it is there. And the more we use the stack, the slower our programs are going to be, okay? That is the point. It slows things down. So back in Unit 3, we started learning about loops and iteration. Love me some loops, love for loops, while loops. You can just get so much done with them. And so now we learn how to use recursion. Recursion will also execute a block of statements many times as you write into the function, but it does it without a loop. And I have to be very careful. Yesterday, I kept stumbling in class because I kept trying not to say loop, and I was saying loop when I wasn't supposed to. So just realize when we look at a recursive function today, it is not a loop. It behaves like a loop, but it's not a loop. So this will give you some insight into how recursion can be used to solve complex problems that are difficult to solve in other ways. One of the keys that we're going to learn about recursion is it breaks a big problem into a bunch of little problems. And sometimes that is a good way to solve a situation. But, and this warning is in the chapter and you will see it in your labs. It's really brought home in the labs we do this week. An iterative solution will almost always perform more efficiently than a recursive function or recursive solution. So basically that means it just doesn't need as much system resources. So when you start writing your own programs, and I hope you guys are already starting to do this, when you're writing your own programs in Python, and it could be in another language, it could be in Java or C#, when you're writing your own programs and all of a sudden you're thinking, man, this thing is running slow. This program should be a lot snappier, much quicker. Well, if your program is running slow and taking up a lot of CPU or memory resources, which you can check on your computer, then you may have accidentally implemented a recursive function. And so if there's one thing we're going to take out of this unit is to be on the lookout for it. And it's real easy to make a recursive function. And it's so easy that you could accidentally do it. And that's the part that scares me. That's the part that kind of hit home with me studying this particular unit, because it would be easy, and you're going to see how easy it is in the coding to create recursion, okay? Because recursion occurs when a function calls itself. Think about that. When a function has a call in the function that calls itself, okay? So when that happens, the recursion can be used to execute the same action repeatedly until a certain condition is reached. And that sounds like the definition of a loop. And it is very close to a definition of the loop, okay? So, but there are some differences between recursive functions and iterative functions. Just remember, when you see an iterative function, when you see a while or for loop, that is an iterative function if it's written properly, okay? So that's one of your first tip-offs is there a for statement or a while statement in there? So we'll start this unit taking a look at an iterative function. We actually have seen this function earlier. It is a perfect example of an infinite loop. It does one print function and then calls because it's iterative, it goes through, it iterates and goes through the loop again. So we define this function, display message, and then just have a while statement there. This is a while loop, while true, print it. Notice there's no false. So if there's no way to do something when this is false, there's no test here, it is an infinite loop. So we go over and over and over and over and over through the print function that says print control plus C to stop. And then eventually we're going to have to press Control C, or this loop will run until your computer dies of old age, okay? So when we hit Control C to stop, and if you're running this in the idle compiler, or maybe another compiler, I'm just more familiar with the idle compiler, but if you stop it, Control C, you're going to see backtrace on the screen in red, and it's going to show you that there is one occurrence of the display message function in memory. One. That's important. Iteration, there's only going to be one, okay? So now let's look at the same idea as a recursive function. It's going to be very simple, but what's going to happen here is we're just going to call the same function over and over. The function is going to call itself. Now, in this case, if you just let this function run and leave, eventually your computer will choke. You will run out of memory and resources and your computer will choke. If you're doing this in Python, you will hit the upward limits of how many times recursion can happen. We'll get to that later in the chapter. And it took me a while to figure out exactly what they were talking about there. But I understand there's a safety net in Python, but that might not be the case in another language. So here is a recursive function that does the same thing as our infinite loop iteratively did a minute ago. So we define the same function and we have the same print function in it, but notice the third line there, and it's in yellow here, that makes this a recursive function because the third line here calls this function, okay? So the same thing happens, the same thing's on the screen in the console, just over and over and over again. When you hit Control C, the backtrace looks a whole lot different. You're going to see a whole bunch of display message functions still hung up in memory. All those display message functions take away resources. And that's the problem with a recursive function. So when we look at this, we see how the two programs do behave differently. These functions differ in the way they use the stack. And that is why we made a big deal about the stack at the beginning of the unit, okay? Because the stack stores all function calls that are in scope. That means that are run within the program in reverse order in which they're called. And we saw back in Unit 5 how we can look at this in the compiler using the debug tools, and we can see those functions in reverse order. Each time a function is called, Python pushes it onto the stack. Think of it as a stack of paper on your desk. You can't see my desk here, but I'm putting a piece of paper here, and then another piece on top of that, and another piece on top of that, and we stack that stack of paper up, okay? And the oldest one's on the bottom and the newest one's on the top, okay? So when the function ends, Python pops, and that's actually not the pop function or pop method we looked at in earlier units, but pop means it runs the function calls off the stack. Now, if this is iterative, it would be just the one function, be very quick. If it is a recursive function, got to tick through all of those very slow. That's the difference. So when the iterative function is called, Python pushes one function call onto the stack. In contrast, Python pushes a call to a recursive function onto the stack each time it goes through the function. And so at the end of the day, that recursive function will never end, and Python will never pop it. So all that stuff stays in memory, stays in the stack. That's not a good thing. So as we have said, the stack requires a lot of RAM, a lot of memory, and eventually it'll use it up, possibly. We'll talk about the safety net in a minute. So an iterative function, on the other hand, could run forever. There's no reason for it to have a safety net. We have to be very careful not to have an infinite loop go forever. That's not good programming. But at the end of the day, it works completely different than recursion. So repeating again, an iterative function will call the function one time, whereas a recursive function will call the function many, many, many times. That's the difference. So we're going to see a bunch of examples. We'll wrap up this unit in just a little while with this puzzle that uses recursion. And it's an example of a good reason to use recursion. I imagine you could write that puzzle iteratively, but it works really nice and very simply. You'll see how simple it is when we use recursion at the end of the unit. So we're going to look at an iterative function and then a recursive function of the same thing. All we're going to do here, we haven't even gotten into the patterns yet. We're just going to add up some numbers, the sum of a range of numbers. And we're going to work with the numbers 5, 0, 1, 2, 3, 4, 5, our upward limit is going to be 5. So if you add all those together, the total is 15. So, this is not rocket science. So we can do this iteratively, very simple, but we can even do it easier recursively. Okay, so let's just see how this works. In this case, our definition is going to be for add numbers. We have one argument or parameter for our custom function here, which is upper. We'll set the value of a variable to 0 named total. So total is going to equal 0. Said that backwards. And then we'll have a little for loop, and that tells us that this is an iterative function. The for loop will use number, the variable number, as its iterator, the end keyword, the range method, and upper will be the upper end of the range, and we're just going to keep adding 1 to it to go through. Okay, so as we go through the range, total is going to increment by the iterator. Okay, and so it'll start at 0, then it'll add 1, add 1, add 1, and go all the way up. And then when we get to the top, when we get to the upper range, the upper limit of the range, then it will return, and it'll be 15. Secondly, we're going to look here at how we could do this with a recursive function. Okay. And you'll see that a recursive function breaks the problem down into small problems until it reaches the simplest possible form of the problem. That is the definition. The simplest possible form of a recursive problem is known as the base case. Okay. Almost always we're working towards 0. All of them in this chapter work towards 0. When we hit 0, we've hit the base case. Okay. So we'll start off with this example, and the simplest form in this example will be the upper limit hits 0. Okay. Once we get there, there's no reason to do any other work. And so that is the base case, the simplest form. Okay. So here is how we do it recursively. And the tip off here, there are 2 tip offs that I can see right off the bat. Oh, no. What did I do? Hold on just a second. I forgot to turn on my magic circle, which just cramps my style. So hang in here with me. Just imagine you're not seeing that, because that's very unprofessional. But now I have my magic circle. So here we go. The definition for our custom function, we're calling it again right here. That's tip off number 1. When you can see that in the block of code, we are calling in some way, shape, or form the function that we are creating. And also there is no for statement and there's no while statement here. This is an if statement. So it acts like a loop, but it's not really a loop, not in the truest definition of an iterative loop. So add numbers, the upper limit, the first line is exactly the same as the previous example iteratively. So if the upper number is equal to 0, then return the upper number. Else clause, return upper plus run the function again and upper minus 1. It'll do it. And so we just keep going through that. We'll go through it 6 times because 0 counts. And in our example, we were talking about upper as a 5. So it'll be 6 times through. And at the end of that, you will have 6 running memory hogging copies of that function in the stack. And that's the problem. And it will not unpack those or pop those, which will releases the memory. It won't pop those many functions until we get to the end of the problem and hit the base case. Once we hit the base case, then pop 6 times, and we get our memory back. So we'll pause right here. Haven't heard from anybody. Am I making myself clear? Do you understand the difference between an iterative function and a recursive function? Anybody have anything to say? Don't understand why students don't want to talk to me, but they don't. Okay, I'm going to assume everything's cool. We'll move forward. I think we've actually covered all this. So we'll call this with 5. The function begins by checking whether the upper limit is 0. It's not 0, so it runs. This point, if it is not so, the base case has not been met. Stops when it hits the base case. That's why it's normally 0. As a result, the code breaks the problem down into adding the upper limit to the result of calling the function with an argument of the upper limit -1. I think I can get it, but need to read and practice it. Yes, sir. That's true, Mr. Matthew. This one takes a little bit of work, and but that's true of every unit. All right. And Matthew, I don't want to pick on you, but maybe this will help you down the road in other classes. But I think you can get more out of the lectures or conversations or whatever you want to call this we do every week. You can get more out of that if you read the chapter before class. And, you know, it doesn't take long to read 12 pages. Just spend 30, 40 minutes reading the chapter before we are in class. And then I think you'll see what we're talking about a whole lot better. And that applies to everybody, not just Matthew. You just reminded me. All right, so back on recursion here, the key is that the addition operation cannot be performed yet because it depends on the result of a function call. And the result of that function call is not known yet. That's why it's called recursive, okay? So that brings us to the term deferred action. And I don't think deferred action is going to be hard for you to remember, because each one of those pieces of paper I was putting on that imaginary stack on my imaginary desk, that was a deferred action, okay? That means that until we hit that base case, until the recursive function hits that base case, all of those cycles, I'm not going to say the L word, but the cycles through the recursive function is a deferred action, okay? Making it academic here, we have to have names for everything. So as we go through the cycle, the second time, the upper limit is 4 because of the -1, okay? The third time through, or would be the third time through, would be 3, and it keeps going. And each one of those cycles through the function is going to end up in RAM. So we keep going until we get to 0. Then, because we hit the base case, we can pop. So this pops all of the previous recursive function calls off of the stack one at a time in the reverse order which they were pushed on to it, okay? And Python is going to add the return value of each of those recursive function calls to the upper variable, and that is why it's called deferred, because it waits till the end when the function is finished running. All right, so 6 times because of 0. A minute ago, I said there is a safety net in Python, and this is a Python thing, probably is in Java and C#, but I don't know. I don't teach those classes. And we don't even talk about this in PHP class. Maybe we should, but we don't. So there's something called recursion depth, okay? If you exceed recursion depth in Python, you'll get a recursion error. So it'll error out instead of using up all your RAM. Typically in Python, it's somewhere around 1,000. That's a lot of repetitions. You might not be able to get to 1,000 depending on how much is going on in your recursive function. But you might run out of RAM before you hit the recursion depth. But if you do hit the recursion depth, and there is an exception, you can write a handler for it so that hopefully you get out of the problem before it locks up your computer. And you're thinking, well, yeah, who cares? Okay, we care because we're working for a company that's paying us a ton of money to go in and solve problems, and we don't want to bring down that big server. I am watching for the second time through Halt and Catch Fire. Have y'all watched that on Netflix? Since there's no football on TV, hardly anything's on TV right now. It's a good time to rewatch some really good old stuff, and thank the world for Netflix, one of the best bargains in entertainment. And so if you haven't watched Halt and Catch Fire, that is, yeah, it's an old AMC series. It caught, it only ran 4 seasons, 4 short seasons, but it's interesting. It's a docudrama. It's not historically correct, but it's kind of a story about these young kids that started in their garage and started all these tech companies, and how they failed and went and started another tech company and made bunches of money, and all that money got spent, and so forth and so on. It's kind of interesting. I like it. Anyway, I don't know why I got off on that, but I was thinking about the computers. You're getting paid all this money, and I just watched an episode. One of the guys, the kind of the pain in the butt guy character in the story, went to work for a big oil company in Texas, and he's running the data center there, and all these big IBM mainframe computers in there. You don't want to stop one of those mainframe computers because of a recursive function. Man, it took a long time to get to that punchline. Okay. So, back to algorithms. Anybody want to talk about recursion anymore? We're going to get back to it, but I think I've done about all I can do to help you understand it. So algorithms, nothing to be intimidated by, but we're going to get into writing some algorithms. A lot of our programming students, by the way, transfer to USC Upstate for years 3 and 4 of their education, and they go over there and do about 1 million projects in Java. That is the only language they care about at USC Upstate. And I've been told more than once that pretty much the 3rd and 4th year of that 4-year program of a 4-year program, it's going to be all about writing algorithms. Okay, so we're getting a little head start here. A lot of math, a lot more math than I've had. You'll have to have that to take that program. So just realize that we're going to try to use Python programming here to solve a problem, to do a task, okay? And we're going to do this first off with a couple of number problems, 2 mathematical problems. You may have actually heard of these. And then the last one is a puzzle. And we'll do the puzzle using recursion. And we're actually going to use recursion for all of this, just to show you that it's not a bad thing. It's just something we have to be careful with. The big plus side to use a recursion is it doesn't take a lot of code to solve the problem. Okay, so it's clean and concise, and our writer of our textbook makes that very clear. But just realize from an efficiency standpoint or performance standpoint, whenever you see those kind of words, iteration is much better than recursion. Now, the first math problem we're going to deal with is factors. And if you took a lot of high school math, you probably did some factors, okay? So first off, we have to know the definition of what a factor is, or factorial number. The factorial of a number is defined as the product of all the numbers that are equal to or less than that number, with the special case that the factorial of 0 is always 1. So our example case is going to be the factorial of 5. The factorial of 5 is 120. But you can figure and calculate the factor for any number, okay? That's the pattern that I was trying to refer to. This is the first pattern we're going to look at. So there's a mathematical notation for factorial numbers, and it's just that you have the number followed by an exclamation point. That means it is a factorial of that number, okay? So let's look at the bottom line here. 5 exclamation point equals 5 times 4, okay? So it's a product of all the numbers that are equal to or less than that number, okay? So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1, which is the factor of 1, okay, still 120. And then for 0, it's also 1. Remember, that's our exception. It's still 120. So that's how we got to 120, okay? So that's our first little conversation piece on factoring, okay? So given the definition of a factorial, you can create an algorithm for computing the factorial of a number, as we just saw. We just need to write code that will do that. And here lies the problem, okay? All of this stuff is fun and interesting, but the logic that you have to go through here is the part that is scary to me, okay? The coding's simple, but the logic of figuring out how to get this to work is a head scratcher. And so if you're intimidated by that, you are not alone, okay? So just get over it. We're all kind of in the same boat. The logic is difficult, but we're going to see how to do it. The book's going to show us how to do this, okay? So we'll just do the factorial of 5 as our example, and we're going to do recursion, okay? So the factorial of 5 can be recursively defined as 5 times the factorial of 4. The factorial of 4 can be defined as 4 times the factorial of 3. You see the pattern? Think about it, bullets 2 and 3 here. The factorial of 5 can be recursively defined as 5 times the factorial of 4. Factorial of 4 can be defined as 4 times the factorial of 3. And it keeps going until we run out of numbers, okay? So the base case here is 0 again, the simplest possible case. Yeah, for sure, this is going to, if you put a big number in here, it's going to take up some RAM. So to show you how simple this is, 2 if statements would do it in our algorithm. If n is equal to 0, then return 1. If n is greater than 0, then return n times n minus 1 point, exclamation point, which makes that the factorial of n, okay? So using that algorithm, we can write a function. We have to write a function so we can run it in Python. And just remember the base case, 0, the factorial of 0 is 1, okay? And that's going to be the end of it when we get to that point. And it always comes out that way. So we have to build that into our function. And the multiplication step, each time we go through the function of n minus 1, that is a deferred action. And it is going to be pushed onto the stack until we hit the base case. So our function is 1, 2, 3, 4, 5 lines of code. We define factorial. We need one argument, which is the number we're going to calculate to, okay? So if that number is equal to 0, then return 1, game over. Else, or else clause, return that number times the factorial number minus 1, okay? And there's our recursion right here. We can see the recursion because we're just going around and around and around without the benefit of a for loop or a while loop. Whenever it pops, we'll have, in this case, 6 again, 1, 2, 3, 4, 5, 6, 6 functions in the stack that have to be popped. Bang, 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 deferred action, and we will get our result. So we can also calculate factorial numbers using an iterative loop or function. And so let's just take a look at that. I think that you know how it works now. I think you know the basis. We had to know a little math. They told us that about the whole how factors work. So let's see how we can do it iteratively. So we'll define the factorial function again with the same argument. And fact is a variable. It's also, well, you see it accumulate in the for statement. Hey, I'm going to go back a slide for a second. I think I skipped something. Anyway, the fact variable is just part of our custom iterative function here. There's nothing magic about the name fact, okay? I guess that's all I need to say. All right, so we defined the function. We set the value of fact to equal 1 because that's the end of it when we get there. And then we go through our for loop for number. Our number is our iterator in keyword range. Num is the lower range, and num plus 1 is the upper range. And so it's going to grow, and each time through, it's going to pop the factorial for that loop. So fact is going to grow. It's going to equal the number times the fact. Okay. So let me think if there's anything else I want to say. We'll return fact here after at the end of each loop. We'll go through that. All right. So that is the iterative way to do the same thing. Any questions? So I want to see what's coming up next. Thought I was right. You might have a question on factorials. All right, our second math problem is going to be the Fibonacci series. And I practiced that. I practiced saying Fibonacci. It doesn't roll off my tongue. It's actually named for a guy named Leonardo Fibonacci, who was an Italian guy, and his 15 minutes of fame was figuring out this pattern in numbers. Okay. Calculating the numbers in this series lends itself to a recursive algorithm that is used in this example. We're going to do this. And if you study mathematics and computer science, you're going to see the Fibonacci series more than once, okay? And this is the one that the student yesterday who has a PhD had seen in an advanced math class he had taken. So we're going to see first the first 16 Fibonacci numbers. These are the first 16 numbers that match this pattern, okay? So in this series of 16 numbers, Fibonacci series, the first number is 0. So we don't have to worry about that. It's going to start at 0. The second number is 1. It's always going to be that way, okay? The first one's always 0. The second one is 1. Every other number in the sequence is the sum of the previous two numbers. To me, mathematically, this is easier than factors by a long shot. This is very easy, okay? So 0 and 1 are always there. And then the third number is going to be the sum of the previous two numbers, the fourth number. So if you go across these 16 here, real quick, like 0 and 1 are kind of locked in. So 1 is the sum of 1 and 0. Got it. 2 is going to be the sum of 1 and 1. 3 is going to be the sum of 2 and 1. Notice we skip 4, doesn't work. 5 is going to be the sum of 3 and 2. 8 is going to be the sum of 5 and 3. 13 is going to be the sum of 8 and 5. And it goes on and on. See, the number gets bigger really fast, okay, up here on the high end. Now, here's the interesting thing from a recursive point of view. Remember, it's the sum of the previous two numbers. That creates two base cases, which creates a really big problem for your computer, because now we got a branch going out, actually a tree with a bunch of branches going out. We have 2 base cases. So it's twice as bad as 1 recursive function, really, if you want to look at it that way. And when you in lab 13.1, you're going to be playing around with this, and you're going to be putting different numbers in the recursive function to see this thing work. And you're going to see that your computer will slow down. I mean, I've got a i7 with 32 gigabytes of RAM here I'm working on today. And Monday afternoon when I was playing around with this, I locked it up. I mean, it basically stopped. And I don't remember what number it was. It was fairly substantial, like 100 or something like that. I think it was 100, and the lab said to try and see if your computer would do it. It just stopped. I didn't want to spend all afternoon on it. So we're going to write a function. It's going to be recursive, and it's going to be named fib, which is shorter than Fibonacci, so I don't have to say that so much. And you will see 2 base cases. One base case is going to equal 0, return a value of 0. The second base case will equal 1. Okay, remember those are locked in. And the whole thing is built on the previous 2 numbers. I mean, the Italian guy was having a good day when he saw this. He figured it out. I don't know if he made any money off of this. So I don't think Fibonacci is a household word. Anyway, for any numbers larger than 1, the function uses recursion to add the previous 2 numbers together. All right. And here it is. 7 lines of code. So if fib or define fib, and n is our variable parameter, it is going to be the number we're going to calculate to. So from a very simple point of view, if ib is n, if n is equal to 0, then return 0. Else if clause n equal 1, return 1. Super easy. That's the 0 and the 1 at the beginning. I think all of us could have gotten that right. But look how easy it is to do the rest. Else clause return fib n minus 1 plus fib n minus 2. Think about it. That's pretty simple. And it is very recursive. We have 2 things going on here. There's branch 1 and here's branch 2. Okay. So if we wanted to put this to work, we could do it this way using the Fibonacci function that we created right here for I in range 10. So we're basically using a for loop to set up the range for Fibonacci to work with. Print our Fibonacci recursive function. And now notice I, the iterator in that for loop, is in the fib function. Okay, so we just changed the letter there, but that's what it amounts to. Should have left it at n. It'd been easier to explain, but that makes n the iterator here. And then changing our end of line character to a comma and a space so that it goes across like we saw in our previous example. So that's how you do it in recursion to get the Fibonacci series. So from a readability standpoint, super elegant. He likes that word elegant, Mr. Murak does. 7 lines of code, easy to understand. From a performance standpoint, this is a train wreck. This thing is seriously flawed. It will, like I said, if you're trying to calculate the numbers to a real high number, it is going to stop your computer. So to start, the top level function calls the fib function with an argument of 5. Okay, in our example, since 5 is greater than 1, fib will make 2 recursive calls. That creates the tree effect. Okay, the left side is n minus 1 is called with a 4, and the right side is n minus 2, which is called with a 3. Okay. On both sides of the tree, the number is still greater than 1, so the function makes 2 more recursive calls. And it keeps going until both branches get to their base case, either 1 or 0, depending on which side you're looking at. Yeah, this seems confusing. Each function has its own local variables. That's what functions do. That's what the stack does. Remember, the stack is storing all of those local variables. That is what takes up a lot of RAM, okay? Now, here's what is the problem, okay? And the book explains this, and you can actually expand very easily, because when we do this, we start creating two branches when we put in 5, okay? We're trying to get down here to the base case. So if we go down this side, we run the fib function for 4, and this side for 3. And notice each time it's run, it branches again. So every single number causes 2 more functions to go into the stack. So as a result, 2, just the number 2, is in here 1, 2, 3 times. Look at number 1. 1, 2, 3, 4, 5 times. Of course, it's going to be in there 5 times because 5 is our number we're working with, the number we want to calculate for. So it is interesting. If you look at 3 is in here once and twice. 4 is only in here once, and 5's in here once. Okay. So, and I say that in jest because we're doubling. But once you get to 3, it is one time through for 4 and 5. So the problem is that fib gets called with the same values and then duplicates an enormous amount of work, okay, when you're looking at big numbers. We talked about fib resulting in the value 2 3 times. Wasn't my observation, it was the book's observation. But what this proves is the number of recursive calls increases exponentially, okay? And that's normally a bad thing. As a matter of fact, our book tells us, and you will actually do this in lab and see if it's true, our calculation for the Fibonacci series bombs out about number 32. If you put the range at 32, you will get to a situation where it probably won't work anymore. Now, we can do the same thing using iterative functions, okay? It's not as pretty. Actually, I think it is, to me, easier to understand, but it works more efficiently. It's got a lot more lines of code. So we'll start off defining the fib function again, same way, and we will use an if statement to take care of the first part of the work. If n is going to equal 0, return 0, else if n equals 1, return 1. So that takes care of the 0 and the 1. And then it's just a matter of shuffling the values of n1, n2, and fib, okay? n1 will start off at 0, n2 will start off at 1, and fib will start off at 0, okay? Then look at the for loop here. This is what makes it iterative. For I, the iterator, in keyword, range 2, because we have 0 and 1 up here, we'll start with 2. And the high end is going to be n plus 1. So we'll start off the value n here. So n plus 1. And then each time through this loop, fib is going to equal n1 plus n2. Okay, so we saw that in the definition of the Fibonacci series. Then we've got to go up 1, right? So n1 is going to equal n2, and n2 is going to equal fib, and that will take us up 1. We see the pattern. That is actually the pattern in this series. And then we return fib. And this will return fib each time through as we go through this calculation. I don't know. When I studied this, I thought the iterative way was fine with me. It worked good, and it doesn't kill my computer. So now to prove our point here, when you are doing your lab, you'll have an iterative version of this code, and you can put in a big number like 100, and you'll see how quickly it calculates. but you do the same thing recursively and game over. It's not going to work so good. So at the end of the day, the takeaway here is that some recursive algorithms rapidly grow to the point of being unusable. Okay. Now, before we get into the last part, we are sailing along here. This is not going to take us the whole class, I don't think. I will ask if there's any questions yet, because the next thing is going to be a major, to me, a major head scratcher. The logic in this puzzle is interesting. So I want to ask an interactive question here, and I'm watching the chat. Has anybody in the class ever heard of the Towers of Hanoi puzzle? Okay, good. You guys are smarter than the guys yesterday. Somebody has actually heard of it in this class. It's an interesting puzzle. You might have heard of it with a different name. Okay. My wife, I always try to talk to her about what I'm doing. And I was telling her we were studying this week, and I told her about the Towers of Hanoi puzzle. And she said, "What does Hanoi have to do with this?" And I have no clue. I guess I should research that. I don't know why Hanoi is important. So maybe by tomorrow night's class, I'll know that. But basically, it's a puzzle. And I'm going to paraphrase first. There's three pegs. On the left peg, which we'll call peg A, there are three discs, and each disc is a different size. There's a big disc, large on the bottom, a medium size on top of that, and then a small one on top of that. The idea of the game is to move all of those pegs over to peg C, moving one disc at a time, and they have to be in the same order, okay? There's actually a couple other rules to this as well. So these are the rules. Move all the pegs from peg A to peg C so they end up in the same order as they were on the original peg, only one at a time. I said that. You must move the disc to one of the three pegs. So you could temporarily put a disc on a peg while you're getting things in the right order. You cannot place a larger disc on top of a smaller disc. That's the rule I always forget. You cannot place a larger disc on top of a smaller disc. So basically we have a 3x3 in our example, 3 pegs, 3 discs. You can do it in 7 moves, okay? And I'm gonna go through this because we need to think about this logically. How would you write a program logically to do this? So we'll start off here, 3 pegs, A, B, and C. Those pegs can be named Tom, Harry, and Joe. It doesn't matter what their name. So A, B, and C. Okay, so we have 3 discs. The red one is the large one. The blue one is the middle size one. And then we'll call that yellow or orange is the small one. Okay. And we want to get all of them over to the third peg in the right order in as few moves as possible. We can do it in 7 moves mathematically. So in move 1, we will take the orange small disc off and put it on peg 3. In move 2, we will take the blue disc off, the middle size one, and put it on peg B. I could get that far. In the third one, we can move the disc off of C and put it on top of the medium one on B because we have the largest one on the bottom. So we're still there. All that's valid. And then on the fourth move, we move the red larger disc over to C. So we finally got one where it's supposed to be. Now in move number 5, and this one is the one that is starting to make my head hurt because the small one's got to be moved back over to peg A to get it out of the way, okay? And then we want to move the medium size over to peg C, the third peg. We got 2 in the right place. And then from peg A, we move the small one over to the top. So easy peasy, right? They stayed with the smaller disc on top of the larger disc, the rule I forget all the time. And we got them all from the left to the right. Now we have two variables here, the number of pegs and the number of discs. In our lab, our third lab, you're going to play around with this by changing the number of discs and see how this affects things. It will also change if you have even number versus odd number discs. That's also part of the problem. So let's see how this happens. We can write, and all of this is going to be recursion. We're not going to do this iteratively, so we really got to figure out how to do this recursively. So the recursive algorithm is going to work this way. We're going to move n-1 disks from peg A to peg B using C as a temp holder. That's the first move. Then move disk N from peg A to peg C. And then we will move N1 disk from peg B to peg C using A as a temporary holder. That just doesn't seem right to me. I've read this over and over and over again. It doesn't seem right, but that's what they tell me. So we'll see how this works. From a programming standpoint, our function is 1, 2, 3, 4, 5, 6, 7 lines of code again. We'll define this function. Move disk is our function. N is going to be the number of disks, okay? Source, SRC, is going to be disk A. That's going to be the left disk. DEST's destination, that's going to be peg 3, or C, excuse me, peg C. So A and C, and then temp will be B because that's the other peg, okay? So if N is equal to 0, return, game over. All the N's have moved through. Else, we're going to move N1 source temp dest, okay? Now, what is that going to do to things? We're going to print N, which is going to be the number of disks, the disk number we're moving from the source to the destination. Then we're going to run the function again recursively. We actually are doing this recursively twice here, okay? So N-1 temp, notice temp is over here on the left to destination and source, okay? So the function is actually working by moving the peg references, but N-1 seems to stay the same, okay? So the function shows how the algorithm can be implemented in Python, okay? The number of disks is its first argument, and the names of the 3 pegs, the next 3 arguments. I told you that. It begins by checking to see if the number of disks is equal to 0. That would be the base case. If we hit the base case, game over. In this function, the function calls for a return statement to end the function. The function uses a return statement to end the function. If there are disks left to move, the function calls itself to move the disks. That's N-1 if the number of disks -1 exists, okay? So the function calls itself to move the disk. The first statement is a recursive call that says move all disks except the largest one, because we have 3 disks, disk N, which is the largest one, from peg A to peg B using peg C as the temporary holder. Remember, those are the variable names in our function. This places one branch of recursion functions on the stack. Then the second statement prints the message for moving the largest disk N. The third statement is a recursive call that says move all of the disks except the largest one from peg B to peg C using peg A as a temporary holder. So if you think about this, after the first move, peg A and B are going to be the temporary holders. This places the second branch of the recursion functions on the stack. When the number reaches 0, Python will pop all the branches off the recursive tree. This results in a symmetric pattern on each side of the number N. Probably would not have known that if he didn't tell us. And so here's the output. There's no fancy drawing or anything like that. It just tells us the moves from the print function that's inside our custom recursive function. And so we can see we're moving disk numbers and then from peg to pegs. And so we were working with 4 disks in this example. Remember, we originally said 3 disks, 7 moves. 4 disks looks like 15 moves. So there's a pattern there. As we add a disk, the number of moves doubles +1. Think about that. So here's the code, and hopefully it impresses you that all this code fits on one slide. I don't think we've done many end of chapter examples in one slide. So all of this is our recursive function that we just saw. So I'm going to think about this again. So we set up the move disk function. N is the number of disks. Source is A, destination C, temp. Okay, so those are the names of our pegs. We know them as ABC, but the program knows them as SRC, DEST, and temp. If n equals 0, return else. We're going to play the game. So move n minus 1. Okay, so that would be n up here minus 1. And then source temp is B and destination is C over here. Print the move. Okay. And then here we change the pegs. We do it again, but we change the pegs. And because this is recursion, it's going to keep going around and around in a cycle here until we get n equals 0. And then it will stop, it'll pop, and that'll be the end of it. So when we write our main function, we have our heading, and we ask the player of the game for the number of disks, okay? And then we run our function. Move disk is our function. Num disk will be n, which is collected right here. Do we change the name of that variable? And we have strings for the names of the 3 pegs. And then we just run our function here, run this recursively here. And then once that's all done, we're not even counting the moves, which I thought was kind of lame. They ought to at least count them. But all the disks have been moved. It'd be easy to add a counter in this. Then at the end, we just do an if statement to make sure this is the main function. So what do you think about that code? Any thoughts? You're going to play with it in lab and get more familiar with it. So hopefully it'll make more sense to you. This is what I was saying with 4 disks, it takes 15 moves. Remember, it was 7 moves for 3 disks. If we add another disk, it becomes 31 moves. So you see the pattern there. Numbers have patterns. And in this game, I guess it's because of the 3 pegs. Not being a mathematician, I can't really say, but it doubles the number of moves +1. The last couple of notes here just explain what the function does that we just saw. So I'll go through this really, really quickly. The Python code begins with the move disk function, and the main function just calls it basically after it knows the number of disks. And you're going to try different numbers of disks in the lab, and you're going to make a little small change to the program. Next, it begins the recursion by calling the move disk function and passing it the number of disks and the names of the pegs. We saw that. Nothing special about the names of the pegs. When Python finishes making all the recursive calls, the move disk function execution returns to the main function and prints the final little message. So to test this, you can run different numbers of disks. Start with a small number and gradually increase. Try odd and even numbers. It will actually change how it calculates Note that the series of moves is different depending on whether they are odd or even numbers of disks. Also note how fast the number of recursion calls grow, okay? Down at the last bullet here, solving the puzzle for 32 disks takes 4,294,967,295 moves. Let that sink in. That's going to take a while. So that's a lot of moves. But that's fun with numbers. Because the number of recursive calls grows, the larger number of disks can quickly make it so the program will not finish in a reasonable amount of time. There's one thing you might think about doing to speed it up, and I think it's just stupid, but okay. Take the print statement out and run the function, run the program, and it might run a little faster, but not much. You'll see the print function does affect the time. So any thoughts about the Towers of Hanoi game or puzzle? We have not had a unit like this, nor will we have another one. This is it for our math, heavy duty math part of the course. It's not a math course. So I hope that you'll find something interesting here. I did not like this chapter at all the first time I read it. It took me a while to understand what I was looking at. And so maybe our discussion today, our talk today, will help you with that. I hope that when you study it this week, it won't be too bad for you, okay? I don't think it's going to take a long time to do the labs, but I think you really need to bear down and study it. You need to read this short chapter a couple of times and read a few parts of these, like the Towers of Hanoi, the Fibonacci series. You might want to read those pages more than once. Our terms list is fairly short, but it hits all the high points. I've tried to bear down on all these terms as we were going through here. And the summary at the end of the chapter, as always, is a Cliff Notes version, which will help you put the words, the key terms into some kind of meaningful sentence, okay? So I think the summary page is an important part of the chapter. We're finishing up way early, which is okay. Gives you more time to work on this. So things to do this week. Take test 4. Today is the last day. So 50 questions, up to 3 of them could be fill in the blank. Mostly, by far, most of them are multiple choice. There's 1 or 2 true false questions in there as well, maybe 3. All right, so read and study chapter 13 this week. You can have these slides and download them off my website, do the topic and do the 2 labs we've been talking about, and then complete the quiz. I don't think it'll take you a terribly long time to do this unit, but study chapter 13 maybe more than once. Okay, now, one thing I want to also remind you is there will be questions from this unit and next week's unit on the final exam. They're not in a test, but they will be in the final exam. That brings us to the end of today's episode. So does anybody have anything they need to talk about? Any questions? Interesting. I'm playing around with my screen here while I'm waiting. And guys say, oh, looks pretty good. Good stuff today. Thanks. Nope, I'm good. Okay. Well, you know where I live. If you need anything, just give me a holler and I will be glad to answer your questions. Other than that, I think we'll go ahead and adjourn. And you guys have a good week. And I will see you next week for our last lecture. Okay, our last one is next week. Okay, and 2 weeks from this week, our final exam. Have a good time, a good week, and study hard, guys. We're almost done. Take care of yourself.